So we're going to dive into section 8.2, which is inverse functions. All right, so our starting point is just to understand what an inverse function is. So first of all, an inverse function, f of x, okay, is denoted by, let me put this in a different color, f, and then you've got that little -1 that looks like an exponent of x. But what is very clear here is that that -1 is not an exponent. Right here, this -1 just denotes that the function is an inverse. That's all. Okay? That's what we're talking about. So let's look at our next thing. So if we've got a graph f of x, okay, and that graph f of x contains the point xy. Well, the inverse of that function that has the ordered pair xy, well, the inverse is going to contain the point yx. So what happens is those ordered pairs in the inverse switch order. The numbers inside of them switch. That's what happens with the inverse. Well, that's pretty cool. Okay, so let's kind of explore this a little bit. So if we have a function right here in green that includes 3 members, each of those members are ordered pairs, 1, 0, -3, 5, 0, 4. Okay, so the inverse of this function is going to still have 3 ordered pairs, but the ordered pairs will be in the opposite order. Okay, and so that would be this in orange is going to be the inverse of the green. Let's look at another characteristic between functions and inverse functions. So the domain of a regular function is the range of an inverse function. Okay, so the domain of f of x is the range of the inverse. And then the opposite, the range of that first function is the domain of our inverse. That's a little bit much to get your head around at first, but it's really just the opposites. All right, so now here's the question for us to really consider. Is the inverse of a function also a function? And our answer to that is sometimes. So let's look at when it is a function, when the inverse is a function, and when it's not. So we've got this thing that's called a one-to-one function. Basically, all a one-to-one function is saying is that that function, the original function is a function, and the inverse is also a function, okay? That's a one-to-one function. So let's look at some examples. So our first example, which I'm going to highlight here in yellow, is an example of a one-to-one function. So remember first, if we have something that is a regular function, so a regular function, then no x's are repeated. And sure enough, we've got 1, 4, 7, 5. Then for a one-to-one function, then the inverse needs to be a function. And so if the inverse is going to be a function, then that means no y's are repeated in the original ordered pairs. So let's look at that. 3, 2, -1, 7. So because the x's are not repeated and the y's are not repeated, that makes this a one-to-one function. All right, let's look at this next example. The next example I'm going to highlight here in green. This one is not one-to-one. Well, let's look to see for our x's. Our x's are all unique. None of them are repeated. Let's look at our y's. Well, our y's are repeated. I've got our 3's that are repeated. So that means it's not a one-to-one function. It's a function, but it's not a one, but the inverse is not a function. So it's not one-to-one. Now, let's look at this last example. This last example is not even a function because our x's are repeated. All right. So let's look at this example that we have here highlighted. Whoopsie. I meant to highlight that, not draw a line through it. So I've got this highlighted in yellow, and I want to figure out if it's a one-to-one function. So I'm first going to look at my x's, and I see that they are all unique. Okay, 2, 3, 4, 6, and 0. Then I look at my y's, and I see 5, 8, 11, -11, and 0. So none of my y's are repeated. So x's not repeated. Y's not repeated. Therefore, we say this is one-to-one function. All right. Well, just like we were using vertical line tests to help us determine whether or not a function was a function, okay? We can use a horizontal line to tell whether it is a one-to-one function. All right. So let's look at this parabola. So when I look at the parabola that's in blue on the left, if I was to draw a vertical line, I could draw a vertical line anywhere in that parabola, and it's only going to intersect in one place. So that means it's a function. But when I draw that red horizontal line, I see that I am intersecting my parabola in two locations. So that means my y's are repeating. That's why it is not a one-to-one function. Let's look at the example to the right. That one is a curve. It's actually a square root function, so it's a curve that starts at the origin. And this one, if I was to draw a vertical line, it would only intersect in that curve in one spot. And then my red horizontal line only intersects in one spot. So because the x's and the y's are not repeated, it is a one-to-one function. Let's look to see if these are functions or not, and if they are functions, are they a one-to-one? So I look first at the vertical line, okay? So I see this vertical line, and I see it just intersects in one place. So that's good. Now I look at my horizontal line, I see that that only intersects in one place. So this is a 1-to-1 function. Okay. Now let's look at our middle graph. I see with my vertical line that it intersects in two spots. Same with actually my horizontal line. So this is not a function at all. All right, let me draw this a little bit more clearly. This first graph here, this is a piecemeal graph where you have two pieces of a graph kind of separated, but they're in the same coordinate plane. So if I draw my vertical lines, okay, they only intersect the graph in one place. So it is a function. But when I draw my horizontal lines, they intersect an infinite amount of times. So it's a function, but it's not 1-to-1. So the inverse is not a function. Okay. Well, let's look at the definition of an inverse function. So your function is considered 1-to-1 if the ordered pairs can be written in opposite order. Okay? That's an inverse function. So I've got f of x, okay, for my inverse. And that actually, it wouldn't be, it'd just be my f of -1, okay? And my first ordered pair would be 4, -3. Then I've got 7, -2. Then 8, 4. Then -1, 11. Close my brackets. My inverse for the next one, for G, is kind of weird because those are doubles, 0, 0, 1, 1, 2, 2. My inverse is going to look exactly like my regular function. And that's okay. It's just what it is. There we go. But they're both still 1-to-1. Well, I can use something called an inverse function property to actually prove that two different functions are inverses of each other. And the way I do that is by finding the composition, the regular composition, and then the opposite composition. And when I find my compositions, they will always equal x, even when I take the inverse. All right, that doesn't even seem like it should make sense. How does that work? Well, let's give it a whirl. So if I've got f of g of x, okay, so that means my f function is kind of my foundation. So I'm going to draw my fraction bar, put a space there where x is, plus 8 in the numerator, 4 in the denominator. Now I'm going to drop in that g function, 4x minus 8. Okay, so if I remove those parentheses, then the minus 8 and the plus 8 become 0. So that's going to give me 4x over 4. My 4's can reduce, and so this is just equal to x. That composition is equal to x. Well, now let's go the opposite direction. Let's find g of f of x. Okay, and so that's going to be I'm going to take my g function 4 times, I'm going to put parentheses, minus 8. Then I'm going to drop in that f function, x plus 8 over 4. Now I can go ahead and reduce. Well, this 4 on the outside of my parentheses, when I multiply it times that rational expression inside the parentheses, or the fraction in the parentheses, the 4's reduce. And so I'm left with x plus 8 minus 8. Well, plus 8 minus 8 is 0, and so that just leaves me with x. So both compositions equal x, and that proves that those are inverse functions. All right, so let's go ahead and do the same thing with problem 5 here. We're going to show that these functions, f and g, are inverses of each other. All right, so I've got, let's just start with f of g of x. So f is my foundation, so that's going to be the cube root of x, and then the minus, oops, that x is supposed to leave that blank. That's going to be underneath my parentheses. I'm just not thinking. Underneath my radical, okay? The minus 7 is outside of the radical. Now, underneath that radical, I am going to input my g function, which is x plus 7 cubed. All right. Anytime your exponent and your index match, that's going to shake out that radicand of x plus 7 in this case, and then I bring down the minus 7. So now that plus 7 and the minus 7, that's just 0. So that means this is equal to x. Now let's take the opposite composition. Let's do g of f of x. Okay, so g is my foundation. And so that is going to be, I'm going to put my parentheses, and then inside leave open parentheses, put plus 7, and then cubed. Oops, let me bring that down. Inside those parentheses, let me drop in that f function, which is going to be the cube root of x minus 7. So that minus 7 is outside of the radical. So let's be careful here. Let's simplify inside of the parentheses before we apply that exponent of 3. So I've got a minus 7 plus 7, which is 0. So this is going to leave me with the cube root of x cubed. Well, my exponent and my index match, and so that shakes out my radicand of x. There we go. Both of my compositions equal x, so that proves that they are inverse functions. All right. Well, how do we find an equation of the inverse of a function? Let's figure this out. We can do this really easily if you follow these 4 steps. So, first thing you're going to do is we're going to replace f of x with y. Then you're going to interchange x and y. Then you solve for y. And then lastly, replace y with that inverse function notation. Okay, so if we start with f of x is equal to 7 over 3x minus 1. step number 1 is replace this f of x with y. That's step number 1. Then step number 2 is you switch places between the x and the y. So the x comes to the outside where that y was. The y comes and takes that x position. Now we want to solve for y. So anytime your variable is in the denominator like it is here, the easiest thing to do is to multiply both sides by that denominator. So that's why I'm multiplying here by 3y minus 1. So the 3y minus 1's go away. And so I'm just left with this x times 3y minus 1 equals 7. When you distribute that x, that's how we get this next equation. All right. So again, our goal is to get y all by itself. So if you add this x, bring it over to the other side, that gets you the 3xy equal to x plus 7. And then you simply divide both sides by that 3x. That's how we get y is equal to x plus 7 over 3x. So we solve for y. Now we just need to put it back into function notation, which is to replace that y with the inverse function notation, just with that -1. And then that shows it's the inverse of that original f function. All right, well, let's kind of do one here. So let's start with this. So our first step here is to replace the f of x with y. So I have y is equal to the square root of x plus 6. Second step is to interchange the x and the y. So literally, the x comes out, the y goes into the radicand. I just switched them. Now I'm going to solve this. I want to solve for y. Well, what I'm going to need to do is I'm going to, like I would solve any radical, raise both sides of my equation to a power equal to the index. And so when I do that, I'm left with x squared equals y plus 6. And now I can solve for y by just subtracting 6. So I get x squared minus 6 is equal to y. My last step is to put it back into function notation. So f of -1 of x is equal to x squared minus 6. All right. So now what I want to do is the next problem. Let's do this one in green. So I'm going to find the inverse. So first thing that I want to do is I want to change the f of x to y. So y is equal to 8x minus 5 over 4. Now I'm going to interchange x and y. So x is going to come out, y is going to go back in that numerator. I just did a little flip, interchange. Now step number 3, solve for y. Well, I'm going to multiply both sides of my equation by 4 in order to get rid of that denominator. And so when I do that, I end up with 4x equals 8y minus 5. Okay, because these 4's reduced. I'm going to add 5. So I get 4x plus 5 equals 8y. Divide by 8. So I get 4x plus 5 over 8 is equal to y. My last step, put this back into function notation. So f of -1 of x is equal to 4x plus 5 over 8. There we go. Let's do one more example here. We'll do this one in purple. So let's start with y equals x squared minus 7. This one, I'm going to go ahead, interchange my x and y. X is equal to y squared minus 7. I want to add 7 to both sides. X plus 7 is equal to y squared. Take the square root of both sides. And so I get right here, let me bring it over a little, the square root of x plus 7 is equal to y. And then I'm just going to put in function notation. F of -1 of x is equal to the square root of x plus 7. Notice when I took the square root of both sides, I didn't do that plus minus thing. That's because right here, it says that x is going to be positive. All right, now, this one's kind of a goofy one. I'm going to summarize this one. So we've got this graph. Let's say the graph right here, y equals f of x, is our blue graph, okay? And the domain, actually, the domain for all of these is going to be all real numbers, okay? And our graph, the red line is going to be the graph of the inverse of that function. What really is kind of unique when you look at inverses is, see this dotted line here. So this dotted line is the line y equals x. And it always goes right through the origin, and it kind of cuts that quadrant 1 and that quadrant 3 in half. That is always going to be what you're going to have, those slants right there, those slant equations that create the symmetry between your regular function and your inverse function. That will always happen. Pretty cool. All right, you have enough information now for you to go ahead and have fun with the homework. So have fun.